Hello, Maisa.
Hello, ma'am.
Hello, Abu Bakar.
हाय मैम अस्सलाम वालेकुम।
Walaikum salam. Hello,
क्या हाल है
Biswa.
मैम आपका?
Allah ka shukr. Hello, Bilal.
Good morning, ma'am.
Good morning. How are you?
I'm fine, ma'am.
Good. What about Chand Khushi? Hello, Chand Khushi. Hello, Fareed.
Hello, ma'am. Good morning.
Good morning.
Assalamualaikum, ma'am. How are you?
I'm fine. How are you?
I'm good, ma'am.
Okay. So, Rana Shehbaz. Hello.
Good morning, ma'am. How are you?
Good morning. I'm fine. Thank you. How are you?
I'm fine, perfectly fine. Thank you, ma'am.
Hello, Sania.
Good morning, ma'am.
Good morning. How are you?
Ma'am, I'm good. How are you?
I'm fine. Thank you. Hello, Cheryl.
Good morning, ma'am.
Good morning. How are you?
Good, how are you?
I'm fine, thank you. Hello, Zaresh.
Hello, ma'am. Good morning.
Good morning. Okay, so let's start. So we are going to do, just a moment. Okay, we are going to talk about chapter number 15, right? So I'm going to share this with you. Okay, so you know that according to the syllabus, right? We have, this is the last chapter, right? So as we have been sharing, this is all available on Moodle as well. And the syllabus, the assessment plan, and the course outline, all this information is available in the Moodle learning management software that we are using, okay? And it's accessible to all of you. Also remember that the assessment plan was updated after the lockdown, so the latest one would be the one that we follow, right? I've been discussing this from time to time, and also this, as I just said, is the last chapter of the syllabus. So once we complete this, the syllabus is complete. And also, this chapter and the last one that we did, chapter 13 and 15, are a part of the graded homework 4, which is coming up. Okay, so please study, practice, and prepare this. This will also be, of course, a part of the final examination. So we are talking about oscillations. So this chapter is about oscillations. So can you please give me an example of oscillations from real life, from your experience, right? So what are oscillations? Yes. Chand Khushi?
Yes, ma'am.
So what are, give me an example of oscillations.
Ma'am, it is a movement backward and forward in the angular motion.
Okay, so yes, let's see. So we're talking about oscillations, right? So chapter 15, which is oscillations. And yes, you've just said that this is to and fro motion, right? Okay, would anyone like to give an example?
I'm like the swing, the seesaw, the movements of water.
First say your, just a moment, just say your name. You'll,
Fareed.
Fareed. Okay, so you said like what? Example?
Swing, seesaw, ripple effect of water.
Okay, that's okay. So swing, you know, a swing is, for example, a child sitting on a, the swing is connected up and then you have a seat and a child sitting on that seat will swing back and forth, right? And this will be a motion that is oscillatory. Then you talked about the seesaw, you talked about throwing a stone in water, right? On a surface of water, you will see that there will be a ripple effect produced, and this will be, the particles will execute up and down motion on the surface of the water. You can see it anytime, right? So yes, that's good, Fareed. Anyone else would like to share an example?
Ma'am, Chand Kushi.
Chand Khushi, yes.
मैम अर्थ क्रस्ट की जो मूवमेंट होती है ड्यूरिंग द अर्थक्वेक वो भी हो सकती है.
Yes, right. So the movement that is experienced, the vibration that is experienced during an earthquake, for example, is also oscillatory or vibratory motion, right? So yes, and you also know that if this if the vibration becomes too strong, it becomes very damaging or very destructive or very dangerous, right? So yes, that's another thing we have to consider, right? So when there's an earthquake, for example, different things start oscillating, like buildings may start oscillating, and that can become very dangerous. And if they exceed a certain amplitude, it can even be very destructive for the structures as well as for the people there. Yes, so earthquakes, okay. Yes, anyone else would like to give an example? Yes. Any other examples? I give you points when you participate, right? These are,
Ma'am,
naam batao. Yes, what's your name?
Abu Bakr.
Abu Bakr, yes.
Abu Bakr, ma'am.
Yes.
The movement of atom within molecules.
Atom or particles, we may say, they also
Yes.
are in a motion, okay. They,
Yes.
for example, electrons are in an orbit around the nucleus, okay, right? And yeah, okay. Other examples? Very simple examples. You don't have to.
Ma'am, clock.
What's your name?
Maisa.
Maiza. Yes, Maiza.
Clock.
Clock. Okay, yes. Clock. For example, if you look at a clock, for example, which is known as the grandfather's clock, you know, there's a pendulum inside that clock that is going back and forth, right? And this is a simple pendulum is an example of.
Assalamu alaikum, ma'am.
Walaikum salam. Who is this?
Ma'am, Sohaib Tahir.
Sohaib Tahir, देर से आकर disturb नहीं करते हैं ना, शुरू में आया करो. Right? So
Ma'am,
this
3-4 मिनट लेट हुआ.
this to and fro motion is, हाँ तो फिर खामोशी से join करो. So this to and fro motion is also oscillatory motion, right? Any other example? ये किसने कहा था? Maisa, right? Maisa. Any other example that you have come across? Yes. Maisa. Okay, what about, okay, we'll see some examples in the book as well. So I go back to the book and I share it again. No, here you have an example that is described. You can go through this. Now, this motion in physics is known as simple harmonic motion. So it's a motion that's repetitive, right? It's repetitive means it repeats itself. So when we are talking about the pendulum, for example, that you have also done in the lab, the swing and the pendulum. What are the properties? You have a small bob attached here, and this is its resting position or the mean position, right? And mean position. And about this position, it goes to and fro on both sides. So the displacement covered on this side will be x, and the displacement covered on this side, let's say, is minus x. Also, you know that when you set this bob in motion, it will reach a maximum displacement beyond which it cannot go, and then it will come back towards the mean position. Even if there's no force, it will continue, right? So this maximum displacement is known as xm. And this is the amplitude. And on the other side, this is known as minus xm. Okay? So this is an example of the oscillatory motion. Again, we know that the time taken for one complete oscillation is known as the time period, which is represented by capital T. And we know that the inverse of the time period gives us the frequency, which is f. Okay. And the units of this frequency are, since it is the inverse of the time period, it is second inverse. And this is also called in the SI system, it is also known as a hertz, which is one oscillation per second. So these are common terms associated with simple harmonic motion. In this case, you can see that this is a simple oscillating system in which you have a ball moving back and forth. You can imagine this to be your pendulum ball. So the pendulum ball is at zero position, which is known as the mean position. Okay. And then as it starts oscillating, it moves towards, let's say, the right. So it is moving towards the right. It reaches, so this is the x-axis. So along the x-axis, if you measure this distance, when we do this in the lab, a very basic experiment in basic courses of physics, in that case, we can ask students to use a chalk to draw this, to mark the mean position on the floor, that's the zero position, and then to mark the extreme positions, and from here you can get the value of xm, which is the amplitude. So here you can see if it's marked, for example, this will be the x-axis here, and here you have the time. So the time, as I said, is defined as the time for one complete oscillation. Means you start from the mean position, you go to the extreme position, and then you come back, right? And then you go to the other extreme position, and then you come back to the mean position again. So when you complete one complete cycle, this is known as one time period, which is capital T. So the time taken, for example, from the mean position to the extreme position is how much? Who will answer this? You get a point for this. The time taken from the mean position to the extreme position is how much? Yes? Who's going to answer this? The time taken from the mean position to the extreme position, which is xm, is how much? कौन आंसर करेगा? Come on. No one? One time period I told you is starting from the mean position, going here, coming back, going here and coming back. Or an easier way, when students are counting the number of vibrations, we tell them, okay, you can start from one mean position, go to the next, and then come back again, and that is one time period. So my question stands, and I'll give you a point, whoever answers it. What is the time taken from the mean position to the extreme position in terms of the time period capital T. Is it equal to 1t? Is it equal to half t? Is it equal to quarter t? Is it equal to 0t? So these are the choices. So please try to answer this. Okay. So this is the times are plotted here. You can see this. You can see that they have considered this 0 position on the x-axis and they've marked it as 0. And then the ball starts oscillating and then it goes towards the extreme position, which is positive xm. It comes back to the mean position, which is 0. It then goes back to the other extreme position, minus xm. And then you can see this corresponds to minus xm. And then it goes back again to the mean position and this process continues. And this is called simple harmonic motion. Also, you can see that they did not start the time at t is equal to 0. Okay, so it's your choice. You can start the time at t is equal to 0, or they have started the time as at t is equal to minus t over 4. You know that normally when this experiment is performed, we start a clock watch to measure this time. So this is an explanation for this motion. And then if you look at this diagram, you can plot this motion in the form taking time along the x-axis and the displacement along the y-axis. So in this case, when you plot this, you get a curve. What kind of a curve is this? What is the name of such a curve? In mathematics, you see these curves in school level mathematics, in simple mathematics. So what is this curve called? What kind of a curve is this? You remember this? Now I've left you with 2 questions and I'm waiting for an answer, okay? Because I will give you points if you answer these questions. The first question was, what is the time taken from the 0 position to the 1 extreme position? That's question number 1. Question number 2 is, what kind of a curve is this? What do we call this curve? Okay, you've studied this, I know, in school level, O level, metric, FSC, whatever you've done before you came here. So you're familiar with this curve. This is not the first time you're looking at such a curve, right? So in this curve, you can also see that you can define the time period, you can define the frequency, and you can see the amplitude. The amplitude is xm. Xm is the maximum displacement from the mean position, which is 0. So these peaks correspond to the amplitude. And you see the peaks are coming on the positive side and on the negative side. The positive side corresponds to xm and the negative side corresponds to minus xm, right? Okay. So, and there's also a description in this caption. You can read this. Just as I described above, the time period is the inverse of frequency. So here you have the time period. And also this motion can be described with the help of an equation. This is an equation where x represents displacement, as we just said, and t in the bracket means that displacement depends on time. So it means x is a function of, the mathematical way of saying this is x is a function of time. And in words, it means that x depends upon time. Xm we know is the maximum displacement, and this is then multiplied with the cosine of this value. So my answer to the above question, when I asked you what kind of a curve this is the curve for a cosine. This is a cosine curve. So you know that cosine is a trigonometric function, and this function in metric or O levels, you must have seen that when you plot this cosine function, you get a shape that is similar to this. Okay. So the maximum value of cosine is, what is the maximum value of cosine? And what is the minimum value of cosine? Think about it and answer it, okay? So in here you have the description of this equation. You can see xt is displacement at time t, xm, the maximum displacement, also known as the amplitude. And this quantity in the bracket is called the phase. Okay, so the phase depends upon omega. Omega is angular frequency. It depends. So f is frequency and omega is angular frequency. Okay, t is time and phi is known as the phase constant. or it's also known as the phase angles. These are the terms related to this equation. And this is an equation in which the sinusoidal function is a cosine function. Cosine function and sine functions are called sinusoidal functions. So that shape corrects, the graph corresponds to a sinusoidal function of time. So now again today we have someone who's trying to enter the class, and as you are all well aware that only students are allowed to take part in this meeting, and students also who use user IDs that correspond to their official names. So whoever this person is cannot be let into the class. Anyway, so I'm going to take your attendance. Please think about the questions I've just asked you, and if you can answer it, you can tell me your name and you can answer it. So I'm going to take the attendance now. Okay, so let's see. So Sarmad, Amar, these students I think are no more in the class. So Abu Bakr,
Present, ma'am.
Fatma, Baba. Okay. Usman Bajwa, Anam Basharat, Muhammad Bilal.
Present, ma'am.
Yes. Hamza Dar,
Yes, ma'am.
Fareed. Fareed just answered a question.
I think so फरीद ने लीव कर दिया, उसका दादा बाबू की डेथ हो गई, उसने भी मुझे
Oh.
मैसेज किया और वो लीव करके चला गया
I'm sorry.
अभी जी.
Okay. ठीक है. Kessler, Zarish,
Yes, ma'am.
Haris, Muaz, Hafiz Ibrahim, Huma, Alina.
Present, ma'am. Alina.
Okay. Hunain, Rana Shehbaz,
Present, ma'am.
Fania.
Present, ma'am.
Yes, Risha. Chand,
Present, ma'am.
Aiza,
Present, ma'am.
Yusuf, Abira.
Present, ma'am.
Okay, Nadia, Nadia Mukhtar, Hayyan.
Yes, ma'am.
Just acha. Hayyan bola, right?
Yes, ma'am.
Okay. And we have Cheryl.
Present, ma'am.
We have Ashreb, Huda, Amelia.
Present, ma'am.
Good.
Amelia.
Bisma, Siddiqullah, Tahir Suhaib,
Ma'am, present.
Talha, Ali Zulkarnain.
Present, ma'am. Talha.
Talha, welcome to the class. Ali
Thank you, ma'am.
Zulkarnain. Ali Zulkarnain is not here today, right? Okay, good. So we come back and we continue. So we have already defined these terms that I've highlighted here. So please study them carefully. They're not difficult, but if they are new for you, so please familiarize yourself with them because these are important and they're very interesting. If you understand them, they're very interesting. If you try to cram them, then you will get lost. Okay, so try to understand them. Okay. So that you can later on apply these concepts. Now you can see these curves are shown for different cases. I would again like to discuss these curves. So I can share these curves in detail to explain them to you. So I am sharing an image with you. So you can see this image, right? Okay. So these are the curves, the sinusoidal curves that I talked about. Nazar aa raha hai?
Yes, ma'am.
Okay, so you can see that, which color should I use? Maybe this one. Okay, so you can see this is a sine curve. Okay, we are not talking about the sine curve at the moment. We are talking about the cosine curve. But anyway, you can see they're similar. Okay, so the red line here, this is what you did in basic mathematics in school, right? And maybe even if you're studying it now. So you can see that if you plot these curves on a graph, right? So I asked you, my question was, what's the maximum value and what's the minimum value of cosine? Can you answer that?
Ma'am, maximum is
Yeah.
1 and minimum is -1.
Who is speaking?
Ma'am, Alina.
Very good, Alina. So yes, so you know that from basic trigonometry, the maximum value of cosine is 1 and the minimum value of cosine is -1, right? Very good, Alina. That's great. So we have been talking about these functions, right? We have been talking about trigonometry. So cosine maximum is +1, as we just said. So this is +1 and the minimum value is -1. The same goes for sine, but cosine has a maximum value at a different angle and sine has a maximum value at a different angle. And that's why you see that these lines are not overlapping each other, rather they are shifted. And this is called the phase angle shift or the phase shift, okay? Or the phase difference. So that's what we just talked about. So here you have the angle. This is the angle. It starts from 0 and then it goes to pi over 2. Pi over 2 is 90 degree. It goes to pi. Pi over 2 is 90, pi is 180, and then you have 270, and then you have 2 pi. You know, when we were also talking about the quadrants, we also talked about these angles, right? And so on the positive side, you have these in radians. You can also plot them in degrees. And on the negative side, you have minus pi over 2 minus pi and so on. So if you look at the cosine function that we are using right now, which is a dotted blue line, you will see that when you are at 0, the cosine function starts from here, okay? And the sine function starts from here. So at 0 degrees or at 0 radians, the cosine function is equal to maximum, which is +1. Oh my God, cancel. Okay, so the cosine is maximum at 0 degrees, and therefore you see that the cosine graph has a maximum value, which is 1. And in our case, we're calling it xm, the amplitude. Okay, and then you see that at 90 degrees, the value of the cosine function becomes 0. And therefore you see that this value here corresponds to 0. Then at 180 degrees, the value of the cosine function becomes minus 1, right? So this is minus, this corresponds to minus xm in our case, minus xm, and this corresponds to xm, and these are the angles or the phase constant, as we are calling them, phi in our case. So they're representing it by x, but in our equation we use the symbol phi. Is that clear now? Okay, now you understand how we got this graph. So I'm now coming back to the book again, so that you can understand this. Now you can see different examples of the graph, and you can see that you have, in the first case, you have these graphs plotted versus displacement. This is the phase angle versus the displacement. So you can see xm in this case. Now red and blue, what do the red and blue mean? So red is an oscillation which has a maximum amplitude xm prime. Blue is an oscillation which has a maximum amplitude xm. So you see that the red amplitude is greater than the blue amplitude, and this continues throughout the motion. So these are two motions that have been plotted on the same graph, okay? So in the second case, you can see that the red curve differs from the blue curve only on that in terms of the time period. The time period is different. So when you talk about such a graph, you know, when you have this graph and when you're plotting it, right, like this, okay, right, you will see that the time period is defined from this position, one complete crest and one complete trough. That's the time period. One time period is like this, okay? And in this case, you can see that the time period is marked here. So if you're looking at the blue line, it's this one. This is one time period. And in this case, you can see that the time period in case of the blue line is greater than the time period in case of the red red line. The time period of the red line is half the time period of the blue line. So these are two motions that are different in terms of time period. So red represents one motion, one oscillatory motion, and blue represents another oscillatory motion. And in the third case is a change in the phase angle phi that we just talked about. So you can see the blue line, the phase starts from 0 degrees, whereas the red line, the phase starts from minus pi over 4 degrees. So that's the difference. So the phase difference in this case is pi over 4. So these are very interesting concepts, and they're not completely strange or new. I'm sure you've studied some part of it. So please study it again with understanding, and then you will understand it and you will be able to apply it to solve problems. Okay. Right. So we talked about omega, the angular frequency, and just as when we were talking about circular motion, we called it the angular velocity. Here we are calling it the angular frequency. And the equation is the same, which is 2 pi over t. So 2 pi is the total, angle you can cover, which is 360 degrees. In the previous chapters, we were calling this theta. So now this is pi. So this is 2 pi over t. The concept again remains the same. And you can also, as you know, that 1 over t is equal to f. So if you put 1 over t is equal to f, then this becomes 2 pi f, and this becomes the equation for the omega angular displacement, right? Again, as we are using SI units, so phi must be in radians. It can also be in degrees in any problem, and for your understanding, you should be clear how to go back and forth between degrees and radians. Okay, so you can just remember the simple that pi radians is equal to 180 degrees. If you know this, then you can calculate the rest, right? Okay. So in this case, we have a graph which is representing the displacement along the y-axis and the time along the x-axis. And you can see that there are different values on the x-axis. In the first case, it's the displacement, that's xm and minus xm. In the second case, it's the velocity. We know that velocity is omega multiplied by xm. So you have plus omega xm and minus omega xm. You remember again, it was similar for circular motion as well. We can also show that oscillatory motion and circular motion are similar. So we use similar terms and similar formulas. Similarly, acceleration, as you remember, is given by omega squared xm and minus omega squared xm. So when you plot these, this is how you get the graphs. And these dotted lines show you the positions for the different values of displacement, velocity, and acceleration at any particular value of phi. So this is one corresponds to, let's say, 0, phi, and then you have pi over 2, and then you have pi, and so on, as I just discussed before. So these equations, this was the equation for omega. This is the equation for the velocity. Okay, as you know, the velocity is obtained by differentiating this expression, and then you have the value for the acceleration, and you arrive at the same conclusion as you arrived before, that A is equal to omega squared x. In this case, you have a negative sign. The negative sign means, again, looking at the pendulum example, whenever you displace a pendulum, you will see it always has a tendency to come back to its mean position. Even if you apply this example to a mass spring system, this is also a simple harmonic motion. And in this case, you will see that if this is the 0 position of the spring, you pull it and you leave it, it always tends to go back to its 0 position. So going back to the rest position is indicated by a negative sign. So again, these are important points that you can look at for your understanding of these concepts. And we can also look at the force law for simple harmonic motion, which is similar to the, which is not just similar, it is actually the Hooke's law that we studied in one of the last chapters. So which was F is equal to minus kx, where k is the spring constant, right? And then you can also write the value of k in terms of the mass and the angular frequency. So these are small formulas that you're already familiar with. Again, for the block spring system. This is the block spring system that we have studied before. This is an example of simple harmonic motion. That's why we're talking about it again mentioning it in terms of the terminologies. And omega is in terms of the spring constant can be written as K over M under the root. We've also solved problems related to this, right? So the time period again can be calculated in terms of these. Okay. So now we have practice problems. You can look at problem number 1, okay? And you can see this is an example of the mass spring system in which the mass is given as 680 grams. Again, you must notice that this is not in the SI system, right? The spring constant is 65 newtons per meter. The block is pulled to a distance of x is equal to 11 centimeters from its equilibrium position, and on a frictionless surface, and then it's released from rest at t is equal to 0. So the motion starts at t is equal to 0. What are the angular frequency, the frequency, and the period of the resulting motion? So angular frequency is omega, k is given, m is given, but you remember to change m to the SI system, right? And then you get your answer for the value of omega in terms of radians per second. Okay. So the frequency can be found by dividing omega with 2 pi, just as we studied above. So you have the value of omega, you divide it by 2 pi, and you get the frequency, and the units are hertz. The time period is the inverse of frequency. We already know that. And therefore, we inverse this and we get 0.64 seconds. And this is written in terms of milliseconds. So it depends. If your answer is in seconds, it's okay, it's good enough. But if it's like an MCQ and it's given in milliseconds, then you can convert it to milliseconds. What is milli? Milli means? Okay, so the amplitude of the oscillation, what is the amplitude? Amplitude is xm in the equations that we are studying. So you can calculate xm as is described. You in fact don't even need to calculate it. You can understand it from the description of the problem that the maximum amplitude is the maximum displacement, which is 11 centimeters. Again, remember that centimeters is not an SI unit, and if you need, you should convert it. Okay, if you're using it somewhere in some formula, because in a formula all the quantities should be in the same units. So now the meeting is going to end. I would like you to go home and study these concepts and practice them so that we are then able to apply these concepts to solve problems. And please prepare for your homework 4. Okay, so study this chapter and the last chapter for homework 4, which I will upload soon. And again, this will help you prepare for the final exam as well. Okay?
All right, ma'am.
Okay.
Okay, ma'am.
Good. So you have this material, please study it and practice it, and also do your lab homework that I have mentioned in Moodle. Practice that as well. That's also a part of this course.